For decades, theoretical physicists have pursued a singular objective, merging the macroscopic laws of general relativity with the subatomic mechanics of quantum theory. The most successful mathematical framework for this merger to date is the holographic principle, and specifically the ADS-CFT correspondence. This illustrates an anti-de Sitter cylinder. Three-dimensional gravitational interactions inside the bulk space are perfectly projected onto a lower-dimensional quantum boundary on the outside. But this mathematical architecture relies on a strict parameter. It requires a negative cosmological constant. A negative cosmological constant creates a universe that curves back on itself. It effectively puts gravity in a box, providing a convenient, finite boundary where the math neatly resolves. Theoretical physicist Juan Maldacena rigorously demonstrated this duality using string theory in the late 1990s. The limitation is that our observable universe does not have a negative cosmological constant. We do not live inside an anti-de Sitter box. ADS-CFT proves that a holographic duality works as a mathematical sandbox. It does not, however, model true astrophysical reality. When looking out over vast cosmic scales and temporarily ignoring the slight acceleration of expansion, our universe is geometrically described as an asymptotically flat spacetime. The cosmological constant is zero. This creates an immediate problem for holography. Without the anti-de Sitter box, flat space extends infinitely in all directions. There is no obvious boundary on which to project the hologram. To map this geometry, physicists use a Penrose diagram. This tool folds that infinity into a finite, diamond-shaped grid while preserving the causal structure of spacetime. Within this specific diagrammatic space, light cones operate under strict rules, maintaining exact 45-degree orientations regardless of how far radiation travels. Following those 45-degree paths outward brings us to the outer edges of the diamond. This surface is called null infinity. Null infinity is the ultimate mathematical destination. Every massless particle and every photon of outgoing radiation in a flat universe will eventually arrive at this exact boundary. To construct a hologram of the real world, physicists cannot rely on a pre-existing box. They must build a completely new, bottom-up framework utilizing the physical properties found exclusively at this null infinity boundary. Deep inside the bulk of flat space, physics is governed by the rigid Poincaré group. You can translate, rotate, or boost your position, and the laws of physics remain symmetrical under exactly 10 finite constraints. As you move infinitely far away toward the boundary, preserving the metric fall-off conditions causes these rigid constraints to relax. At null infinity, the 10 Poincaré symmetries expand into a much larger infinite-dimensional symmetry group known as the BMS group. The foundation of this infinite group is a geometric action called a supertranslation. A standard translation moves all of time forward equally. A supertranslation shifts time by a different amount, depending entirely on which angular direction you point toward in the sky. For decades, these infinite symmetries were dismissed as mathematical redundancies, gauge artifacts with no impact on physical reality. They are, in fact, real degrees of freedom. These angle-dependent time shifts at the boundary directly govern the laws of radiation and particle scattering inside the bulk of the universe. The mathematics of supertranslations are abstract, but they leave a distinct macroscopic signature that we can observe. Modern gravitational wave detectors use massive test masses suspended in vacuum pipelines, waiting for passing radiation to cause microscopic displacements. When a wave ripples through this grid, the masses oscillate. General relativity predicts a secondary phenomenon, the gravitational memory effect. After the wave passes, the masses come to rest at a permanently altered distance. This signals a permanent reorganization of the spacetime metrics vacuum state. Isolating this permanent low-energy shift is a primary objective for highly sensitive space-based interferometers in the near future. The classical gravitational memory effect is exactly how an abstract supertranslation at the boundary of spacetime physically manifests in the real world. To see how this macro-scale displacement governs the subatomic world, we have to look at quantum field theory. In particle physics, scattering events are constrained by soft theorems. These are universal, mathematically rigid rules governing the absolute lowest energy limit of particle emissions. If you add a zero-energy, or soft, graviton to a quantum scattering matrix, it alters the initial and final states of the particles in a highly predictable manner. As illustrated in this tripartite diagram, the complex mathematics governing the quantum soft theorem and the classical gravitational memory effect are completely identical. In theoretical physics, a ward identity is the mathematical bridge that mandates a conservation law must correspond to a physical symmetry. Tracing the math reveals that the soft theorem is exactly the word identity of the BNS asymptotic symmetries. This is the IR triangle. Low-energy quantum scattering, the permanent displacement of classical detectors, and infinite spacetime boundary symmetries are mathematically proven to be three faces of the exact same physical phenomenon. With this unified framework, physicists have the foundation to build a working hologram for flat spacetime. Beyond super translations, the infinite BMS group also includes super rotations. These strictly enhance the Lorentz group symmetries at the null boundary. Taking a spatial cross-section of null infinity isolates these super rotations. This slice yields a perfect two-dimensional surface called the celestial sphere. These super rotations yield Virasora symmetry. The conformal grid stretches and scales, perfectly preserving the local angles of intersecting lines. These geometric transformations define how a system responds to local scaling and rotations. In 2 dimensions, this mathematical structure is so restrictive that it dictates the entire dynamics of a system, the defining characteristic of a conformal field theory. The infinite asymptotic symmetries of 4-dimensional flat spacetime mathematically force its boundary to behave exactly like a fully functional 2-dimensional quantum system. The final step in the celestial holography program is translating the bulk, 4-dimensional physics of the universe directly into the language of this 2-dimensional sphere. Traditional quantum scattering matrices calculate states based on particle momentum, which does not cleanly map onto a spherical boundary. To resolve this, physicists use the Mellin transform to convert 4-dimensional scattering elements from a momentum basis into a boost basis. It scales out the particle's energy variable, converting it directly into a conformal scaling dimension, positioned flat on the 2-dimensional surface. By taking collinear limits of these newly mapped surface points, theoretical physicists can extract vital operator product expansion data, exactly as they would in a standard 2-dimensional conformal field theory. By utilizing infinite asymptotic symmetries and the IR triangle, celestial holography bypasses the need for an anti-de Sitter box. It provides a mathematically rigorous, bottom-up framework for encoding 4-dimensional quantum gravity onto a 2-dimensional hologram.